Quasars, and it's by Vicky Fawcett. So again, no real announcements to make. So I just leave you to take it over.
Thanks very much. Thank you for having me. So yeah, I'm currently in my final year of my PhD here at Durham, working with Dave Alexander, looking at red quasars and whether these could be a missing link in galaxy evolution. So I don't have a clicker, so sorry about rushing back. Yeah, so just a little bit about me and like how I came here. So I did maths and physics at the University of Warwick from 2014 to 2018, where I did an integrated master's. So I stayed there to do my master's project, which, if anyone knows the astro department at Warwick, it's very much just exoplanet centric. So I did a master's in exoplanets, looking at the irradiation of exoplanets due to X-rays by their host stars. I then decided that was fine. I definitely liked research, but planets were a bit dull, and I wanted something a bit more exciting. So then I got an offer to do a PhD here at Durham, looking at quasars and more kind of extragalactic astronomy. So before I go into what a quasar is, I'm going to start from the basics, but quite quickly build up. So hopefully everyone here knows what a black hole is. They're incredibly dense objects, so dense that not even light can escape, which is why they're called black. And they're formed from the collapse of massive stars. So a star about 25 times the mass of our sun, when it gets to its the end of its life, it will collapse down into a small point and form a black hole. And there's two important parameters for black holes. There's the event horizon, and this is essentially the point of no return. So once you're in the event horizon, even if you're in a rocket traveling at the speed of light, you won't be able to escape. And also the accretion disk. So in this this is a simulated image. It's actually taken from the film Interstellar, but these the kind of black hole imagery from Interstellar was kind of based on these supercomputer simulations of black holes. So this accretion disk is just this very bright disk of matter that orbits the black hole. So because the sun has gravity, planets orbit the sun, a black hole has an immense amount of gravity, so you get this material that is orbiting it at great speeds, and this causes friction between the particles. The friction causes heat, which causes light. So when we talk about observing black holes, obviously we can't see black holes, but what we can see is this surrounding luminous disk. So this is the only bit of kind of thinking I'll get you to do, thinking about the size of a black hole. So I've just said that stars about 25 times the mass of our sun collapse down into a black hole, but say we just had the Earth and we collapsed the Earth down, how small would we have to collapse the Earth down to form a black hole? Essentially, how dense an object would you have to make in order for it to form a black hole? And I think this is in one of the lecture courses actually at Durham, so maybe some of you would know. I won't ask you to call out, but just like think about it for a second. And the answer is about the size of a penny or a marble, because some 6-year-old did point out to me that a penny is two-dimensional. But anyway, so you take all the mass of the Earth and you crush it down to the size of a marble, and then you would form a black hole. So this just kind of shows you how incredibly dense these objects are. So how do we know black holes exist? You might think of a few ways. The first one is binary black hole systems. So these kind of come in two flavors. You can either have a black hole with a companion star, or you can get black hole binaries. And both of these methods, we can indirectly infer that a black hole is there. So starting off with the binary black holes, these are also known as X-ray binaries, and I'll explain why. So this video shows, here's the black hole where you can see this bright disk of matter, the accretion disk, and here's a large blue companion star. And you can see that the black hole has so much gravity, it's actually stripping the star away. And then this kind of fueling of the black hole creates these immense X-ray jets, which we can then, which is why it's called an X-ray binary. We can measure these powerful X-ray events and know that it's this X-ray binary type system. And therefore, we can infer a black hole is in this binary. the other method to look at black hole binaries is gravitational waves. And I'm sure you all heard of this. In 2017 was the first detection of a gravitational wave. It won the Nobel Prize in Physics, actually by the same Kip Thorne, who did the work for the film Interstellar, just a fun fact. So what happens, I'm not going to go into gravitational waves, it's not my area and it's very complicated. But as you get two black holes that orbit in and they get faster and faster and eventually merge, this actually creates ripples in space-time, which we can measure here on Earth using LIGO, Virgo, or in the future, LISA, which is going to be the space-based one. And this is a bit hard to see, but this is just kind of showing these ripples, which actually change the distance, kind of the length of things. So LIGO and Virgo work by like shooting a laser and measuring the distance between these two kind of points. And we can actually see this change by a very small amount, and we can then know that there's a black hole system that's merged. But what's really cool is just from this, we can also infer the starting mass of the two black holes and the ending mass. And this probably needs updating, this masses in the stellar graveyard kind of plot, which shows all the black hole binary systems that LIGO and Virgo have discovered. And also, I won't go into it, but the interesting kind of double neutron star systems, or potential neutron star, maybe intermediate black hole system. Okay, so that's all I'm going to say about gravitational waves. And then finally, another way that we can just determine that black holes exist is by watching the orbits of stars and things close by to it. So I'm going to show you a video zooming into the center of our own galaxy, where we can then infer that there's a supermassive black hole called Sagittarius A star in the center of our galaxy. So finally, this is actually some proper data. So these are actually images. And so all of these points are stars, and we're zooming into the center. But it's actually really difficult to observe the center of our galaxy just because there's so much dust, gas, and stars in the way. So as we get closer, we see like the quality of the images become worse because it's just more difficult. But then what you want to look out for, we're right in the center, is there'll be a few bright objects, which are stars right in the center of our galaxy. And it's a little movie taken from about 10 to 15 years worth of observations of the center. So we're almost there. Okay, so these points are the stars at the center of our galaxy, and this one in particular is a cool one to look at. You can see it has a very eccentric, fast orbit around seemingly nothing. So from the orbits of the stars, we can then actually do some physics and work out how much mass is enclosed in these orbits. And what we find is that it's about a million solar masses. So in a very small space, there's about 1 million times the mass of our sun, which we can't really see in the optical. So we can then infer the only known system this can be is a supermassive black hole. And then finally, we actually have direct evidence. And the first time I gave these talks, I couldn't include this slide, so it's really nice to actually add this slide in. I forget when this was done, maybe 2019. I don't know, time's an illusion. But we now have our first ever image of a supermassive black hole. So this is a supermassive black hole at the center of a nearby galaxy, M87. Although nearby it's still 55 million light years away. And what you're seeing in this image is the shadow of the black hole here, and then the bright kind of ring is this accretion disk, this really luminous disk of matter. And just from this image, you can actually do a lot of physics, and they worked out that this supermassive black hole is 6.5 billion times the mass of our sun. So I don't know if you remember when this kind of came out and it was all over social media. I thought it was probably the biggest scientific breakthrough of the last 10 to 20 years, one of them. But all over my social media was just people complaining that it's just some fuzzy image. But yeah, So how was this taken? So it was taken with a telescope, well, called the Event Horizon Telescope Collaboration, and it was taken in radio. And when you have radio telescopes, you can essentially link them up together, a bit like a big interferometer, and create a bigger telescope, essentially. So what the EHT is radio and submillimeter telescopes all around the world, one in Antarctica, Chile, Hawaii, I forget the others, but you can see North America and Europe. So I think it's about 7 or 8 observatories around the world. And by linking up all these telescopes, they basically made an Earth-sized telescope. And the resolution of this was so good that if you had a credit card on the moon, you'd be able to read the numbers off using this telescope. So over 4 nights, they took images of this supermassive black hole and then used basically a big supercomputer to stitch together all of the images, which is a little bit more involved, and it's quite interferometry is a bit of a dark art trying to piece together different telescopes. And this isn't it. They've been taking data of 2 more supermassive black holes. One of them is Sagittarius A star in the center of our galaxy, and I was told that paper's coming out this year, some point. So maybe at some point this year we'll see another lovely image of a supermassive black hole. And some people do say, why didn't they just start with the center of our galaxy? It's a hell of a lot closer than 55 million light years away. But the answer is kind of what I alluded to earlier, which is it's really difficult to take observations at the center of our galaxy because we're looking through the disk of the galaxy. So there's just a lot of stuff in the way. Okay, so now moving kind of into what I actually research, which is something called active galactic nuclei, or AGN. And an AGN consists of a supermassive black hole surrounded by an accretion disk, this luminous disk of matter, but this accretion disk is so bright, it outshines the entire galaxy. So you see kind of images of Andromeda, or simulated images of what the Milky Way looks like, and it's this beautiful kind of blue spiral galaxy. AGN are more appear like point sources on the sky because the center is just so bright it kind of outshines all the stars in the galaxy. And then we say that a galaxy is an active galaxy if it contains an AGN. So for example, the Milky Way contains a supermassive black hole. It will obviously have some kind of accretion disk, but it's not an active galaxy. And this is just because there's not enough stuff at the center of our galaxy that's fueling this black hole. So it's just not kind of energetic enough for it to be an active galaxy. So at least at Warwick, we one of our lecture courses had this image in. This is like the textbook image of what an AGN looks like. So you have this accretion disk with the supermassive black hole. Then you have slightly further out what's called a dusty torus, as it's known, although this is a bit controversial at the moment. A lot of work's been going on to, is there a dusty torus? Is it a dusty cone? I don't know. And then you sometimes get jets, but you don't have to get jets in an AGN. And I'll ignore the broader narrow line region. But what happened was when they first discovered AGN, they started discovering lots of different types, ones that are bright in the radio, ones that have different, look very different in spectroscopy, so like spectral features. And they started kind of classifying them as lots of different types of objects, and it actually became known as the AGN Zoo. There was just so many of these different classifications. So what happened in 1995, a couple of guys came along and came up with this unified model of AGN. And this suggests that all these different weird types are intrinsically the same objects. They all look like this, but we're just looking at them in different angles. So you can imagine if our line of sight, our telescope is looking up this jet, we're going to see something very different from if we're just looking at the accretion disk or if we're looking through this dusty torus. But the main thing you need to know about this unified model is when we talk about quasars, or at least unobscured quasars, we have this view like directly at the accretion disk. So maybe this explains a bit more. So this is an active galaxy. I know it's a bit bright in here. So you can see the center's really bright. And now we're going to zoom right into what's called the nucleus, the center. Well, what you're kind of not seeing at the moment is that we're now looking through this dusty torus. So it's kind of blocking out most of the light of the accretion disk. So if we were use a telescope and look at it right now, we're just going to see all this kind of dust and not as much as the light, the really bright light from the accretion disk. And now our kind of viewing angle is moving above this dusty torus. So we're going to be looking directly down onto this accretion disk. And again, you're going to see something a lot different. And this movie is actually to illustrate that this dusty torus we think is, well, the model's called the clumpy torus model. So it thinks that instead of this smooth distribution of dust, which people used to think is the case, and this really simplistic image I showed you in the textbook, which a lot of astronomers hate actually, we think it might actually be more kind of like clumps of dusty clouds. Okay, so what is a quasar then? So simply, a quasar is the most powerful type of active AGN. So it's the most luminous, it's one of the brightest objects in the universe. So the most powerful quasars that we've observed have luminosities about 10 to the 41 watts, or about 1,000 times greater than the brightness of the Milky Way. So imagine, taking 1,000 of our own galaxies, kind of putting them all together, and that's how bright a quasar is. And just a note, they were discovered in the 1960s, and when they were discovered, they were just seen to be this kind of star-like object that was really bright in the radio. And people didn't really know what they were, so they called them a quasi-stellar radio source, so star-like radio. Although now we know that they're a type of AGN, and yes, they can be bright in the radio, but they don't have to be, and they're actually bright in a lot of wavelengths. So some people also refer to them as quasi-stellar objects, or QSOs, because they're trying to move away from this kind of like archaic definition. But I think a lot of the time in astronomy, things get named when we don't really know what they are, and then the name just sticks, and and it can get a bit confusing. So so why are quasars useful? Why do people study them? So one main reason is for cosmology. So because quasars are so bright, we can see them really far away. So simply put. And in astronomy, when you look at something really far away, you're looking back in time because of the time it takes for the light to travel to Earth. So what cosmologists do is they use quasars essentially as lampposts looking back in time to try and then piece together how we got from the Big Bang to the universe we see today. So they are very useful to test kind of galaxy models, universe kind of evolution, and they're also probes of dark matter, but I won't go into that. And essentially, I'm not a cosmologist. I don't really care about cosmology. It's cool, but especially if we find dark matter, sure, that would be great. But I'm an observational astronomer, so I actually like to look at quasars for the physics of the quasars and looking at their properties. So I had to update the slide recently, last year. So far, the most distant quasar we've ever discovered is J0313-1806, and this was discovered, I think, the 12th of January last year. And I need to double check this, it could have been exceeded, because since we're getting these great new telescopes, and I'll talk about one of them at the end of my talk, it's only a matter of time before we can just kind of blow this out of the water. But so far I believe this is the most distant quasar, and it's a redshift of about 7.5 if you're into redshift. If not, like everyone that isn't an astronomer, a redshift of 7.5 is about 13.6 billion light years away, which is about 1.3 times 10 to the 23 kilometers. I can't even remember how, I did learn how to say that number one time, but it doesn't really matter. And so if you imagine if we've gotten the fastest kind of rocket we know, or spacecraft, which is I think the NASA solar probe, which goes at about 150 kilometers per second, it would take this many years to travel to that quasar. And this is very simplified, but it's just to kind of like get a handle on, you know, I guess how big space is essentially. But 13.6 billion light years away also, it means that it's incredibly early on in the universe. I believe only 700 million years. Yeah, okay, cool, I got that right. So this quasar, we're looking at it only about 700 million years after the Big Bang. So it's incredibly early on in the universe history. And this is just showing the abstract from the actual paper that came out. And these incredibly large supermassive black holes, these quasars at a very early time, have kind of challenged a lot of black hole growth theory in like recent years. So this is only 700 million years after the Big Bang, and it's a black hole of mass, 1 billion solar masses. And I've highlighted just this sentence here where it says that the existence of such a massive supermassive black hole, only about 700 million years after the Big Bang, significantly challenges theoretical models of supermassive black hole growth. So what this is saying is that we don't think that black holes can kind of grow at like an unlimited speed. We think there's a cutoff of how much kind of, I guess, stuff that can accrete onto a black hole at a time. So you could just do some simple maths when you go, okay, so let's just say this black hole formed really early on in the universe, and it's been accreting at the maximum limit. So it's been growing at the maximum speed for the whole time until we've observed it. How large should this black hole be? And it's nowhere close to 1 billion solar masses. So people just aren't sure how you grow such a massive, supermassive black hole so early on in the universe. And there's a lot of like cool theories that I won't really go into, but you can talk to me about it afterwards. So, I mean, a simple one is just that our like simplistic cutoff of how fast you can grow something is just too simple. It's that kind of like assume a spherical cow in a vacuum kind of thing. So, you know, maybe we've just got it a bit wrong, or maybe there's a lot more kind of black hole mergers, because if you get two black holes that merge, that's kind of the quickest way you can increase the mass of a black hole. And the final thing is either these population 3 stars. So these are these theoretical kind of first stars that are incredibly massive, although people look for these and still haven't found any evidence of population 3 stars, or direct collapse black holes. So instead of going to, you know, collapsing some dust and gas and going to a star, then collapsing the star to get a black hole, you just have so much kind of gas and dust, and it's so dense and it cools so quickly that it directly collapsed into a black hole. And we think that if you do it this way, instead of forming a star first, you can maybe produce larger, what we call seed black hole masses to start with. So basically a larger starting mass in order to grow it. But anyway, this is still an open kind of question, and a lot of people are looking at simulations and models of how to grow massive black holes. Okay, I know we're halfway through, but I'll now talk about red quasars, which is what I like to do. So most quasars, when you look at them in the sky, are very blue. In fact, a lot of kind of surveys that are searching for quasars, they kind of look for things that look kind of star-like, which we've already established is what a quasar looks like, and has blue colours. And if you see something incredibly bright, very blue, kind of point-like on the sky, they go, that's probably a quasar. But we've, and the reason they're blue, is that if you remember this unified model of AGN, a quasar has this unobscured view to the accretion disk. And the accretion disk the light peaks in the optical to UV. So the accretion disk is incredibly blue, which is why quasars tend to be blue. But we found a small subset that show much redder like optical colors, and these are what we call red quasars. And we think that they're red because there's some amount of dust. So an example of this is I've shown a nice picture of the sunset, and sunsets are red because the sun is low in the sky, this light has to travel through more of the atmosphere, this scatters the blue light, sunsets appear red. So we think very simply the same thing's happening in red quasars. There's some amount of dust that's scattering the blue light, and so they appear red. And just a little plug, a paper that should be published in the next month, I kind of proved that red quasars are red due to dust. Just to, it seems like a really kind of simple thing. I studied, like, here are two optical images I've taken from a survey of quasars. The left is a blue quasar, the right is a red quasar. They're pretty unremarkable, but all we're looking for is a quasar that shows red optical colors. So I guess the question you might have, and it's a lot of my friends have, is what's the point? Like, so what that they're red? Why have you spent 4 years studying red quasars? So one of the reasons is there's been kind of a long debate on how red and blue quasars kind of relate to each other. And the two main scenarios are orientation or evolution. So I'll just go through. Okay. So this is a similar but a bit more involved diagram to that unified model that I showed you. So you know the unified model says that if you're into AGN, this shows the different types and the different kind of viewing angles. So in this, a lot of people initially just kind of thought, well, if a blue quasar has this unobscured view to the accretion disk, maybe a red quasar is this line of sight where we're kind of grazing through this dusty torus. That's where we pick up the dust. That's why they look more red. So in this scenario, a red and a blue quasar are just intrinsically the same object. We're just looking at them at slightly different angles. So I am kind of like hinting which one I believe by putting this, again, a little Durham plug here. But the other scenario is this evolutionary scenario. And this is taken from a former PhD student, Vizelka Klint's 2019 paper. So this evolutionary scenario suggests that maybe we start with, say, two galaxies that merge. This obviously creates a lot of energy, a lot of dust that means there's a lot of star formation. So you have a starburst phase, and then eventually this ignites a quasar, but it's still very dusty from kind of the activity before. And this is our red quasar stage. And then through maybe winds or jets, kind of outflows, we like blow away the dust, and we're left with this unobscured blue quasar. And then eventually this blue quasar will just run out of fuel at the center to fuel the quasar, and so it just kind of dissipates into a dormant normal galaxy. And that there is a lot of evidence for this kind of evolutionary scenario in different different objects. And kind of a fun one that I like to think of is that I don't know if anyone's heard of the Fermi bubbles, but there is above and below the Milky Way, there's a little bit off top, but above and below the Milky Way, there's these kind of bubbles of gamma rays that have been observed. And people think that maybe if you imagine like this is the Milky Way, these are the gamma ray bubbles that kind of perfectly go where you think maybe a jet would be. So we think maybe this gamma ray emission is relic emission from an AGN phase that the Milky Way went through, like, many billions of years, millions of years ago. So in my PhD, I've been kind of trying to test between these two scenarios. So how do we select red quasars? So how we do it, there's a few groups looking at red quasars. We use the Sloan Digital Sky Survey, or SDSS, and this has an optical quasar catalogue, so quasars selected in the optical, and the data I used, the catalogue had about 500,000. The latest catalogue's just come out, and this has 750,000 quasars. And this plot here is showing G minus I, so G and I are two filters. So two kind of magnitudes, and then when you take the difference, you have a color. So this is essentially color, where higher values are redder colors versus redshift or distance. And then it's quite a simple thing we do. Some would say maybe slightly arbitrary, is we then select our red quasar sample as the top 10%. So the top 10% reddest quasars are all redshifts. And we do bin this up in redshifts because, as you can see, and as you could imagine, you get redshift effects in terms of reddening. You know, something further away is going to look redder just because of redshift. We then, importantly, choose a control. I'll also refer to it as just the blue sample as the middle 50%. And this is something that previous work hasn't done. Normally, they'll just select some red quasars, look at the properties, and then they'll produce a paper going, oh, you know, red quasars show this. But they won't really have a good control sample, so it's kind of meaningless looking at some objects and saying that they have these properties when, you know, you need to actually compare it and see, are they actually different to the normal, you know, control blue quasars, or are the whole population kind of shows similar quasar properties? Okay, so in my research, it's kind of been split into two parts. First of it has been looking at radio data. So this was taken from my paper in 2020, and it's a bit involved graph, but essentially this graph showing radio detection fraction. So how many of the red and the blue can we observe in the radio compared to the full sample? And this is radio flux, so radio brightness kind of getting more bright this end. And then I looked at 3 different radio surveys, which is why it's split into 3. But the red line shows the red quasars, the blue line is the blue quasars. And then this panel down here is the radio detection fraction of the red divided by the control. So essentially the radio enhancement of the red quasars. And what you can see is that it's larger than 1 for all fluxes. So what we're showing here is that we find there's increased radio emission in red quasars. And this is important because it can't be explained by the unified model. So if red and blue quasars were just intrinsically the same object, we're just looking through more of this dusty torus, we wouldn't expect any difference in the radio properties of the kind of average population. And this is because radio is not affected by dust, because, I mean, if it was, you wouldn't be able to listen to the radio in your house because it would get blocked by your house. And if anything, if you imagine, again, have this unified model picture in your head again, if a blue quasar were looking more kind of directly straight onto the jet, which tends to be, this jet carries a lot of the radio emission, like the majority of the radio emission, then you might expect the blue quasars to have enhanced radio emission because you're looking more down the line of sight of the radio jet, and so you get Doppler boosted. But anyway, we find the complete opposite, which just, it means that there's something kind of different going on. There's some fundamental differences between red and blue quasars. So red quasars could be this special population. The next thing I did was looked at radio morphologies. So this is just what the shape of the radio emission looks like. And here I've got 4 radio images of quasars, and I can then categorize them into 4 different categories. So there's faint, where the radio emission is just too faint for us to say what shape it is, essentially. Compact, when it's unresolved at the resolution of this radio survey. Extended, where we can definitely see a little bit of kind of extended features. And then FR2, which is just this this classification, which means there's 2 kind of distinct lobes, which you can see here. And these images are taken from the faint images of the radio sky 20 centimeters of the first radio survey. And this was the data used by the former PhD student, Lizelka Klint's 2019 paper. And then in my paper, I used a couple of deeper, higher resolution radio surveys. So just to show the difference, these are the exact same objects, but in this higher resolution data. So in the compact one, you can actually see there's a bit of an extended tail. This is my favorite, where we're actually resolving now 2 lobes. So with this work, I then kind of took all the red and blue, and I actually just visually inspected all of the radio data. I know we're moving on to machine learning, but we weren't quite there with my study. So we did human learning and just categorized them ourselves, and then saw what fraction the red and the blue fall in each category. And again, if they're intrinsically the same object, there's no reason to expect that the radio emission would, well, one, be enhanced, but two, look any different between, there should be the similar number in each category. But we don't find that. We find red quasars prefer to have this small scale radio emission. So they're more likely to be detected in the radio, but when you look at their radio images, they're not these like massive radio galaxies, spectacular jetted systems. They're normally very compact and unresolved. So this could suggest, this does actually tie into this evolutionary scenario, because if red quasars are a younger phase, then maybe if this is a small scale jet, it just hasn't had the time to grow into this like larger scale jet. Its smaller scale radio emission could also be caused by winds as well, and that's kind of a current working theory we have that links the dust and the radio, is that there's red quasars just have a dustier environment, and there's these winds, or what we call frustrated jets, which kind of slam into this dusty environment. This causes shocks, and then the shocks is what causes the radio emission. So that's basically what I just said. We think dusty winds might be present in red quasars, but this is kind of my next project is confirming that. That's just a theory. And this is, well, I say in one of our collaborators, Gabby Calista Rivera, last year, actually did produce a paper that does show evidence that red quasars have dusty winds. A little bit like this, it's hard to see, but this is the dusty torus. And then kind of these polar winds is what we're talking about, where you're kind of blowing off dust above and below the kind of center. Okay, and then just because I tease this, but I won't go into too much detail, because essentially this is what we call a spectra, and a spectra is just light at different wavelengths. So you take light and you split it up into different wavelengths. So this is UV, optical, near infrared. And then what you see is these different, what we call emission lines, which is these bumps in the spectrum, which tells us these different kind of elements there. So this is hydrogen alpha, oxygen 3, hydrogen beta, magnesium 2, carbon 3, and carbon 4. And then measuring these emission lines tells us something about the properties of the spectrum. And what this is showing is, in blue is a blue quasar spectrum, and in red is some red quasar spectra. And what's interesting to know is they look quite similar until you get to the UV end, where you then get this turnover. And this is kind of telling us that dust is present, because dust kind of makes, induces this turnover. And from, this is the work that I've just submitted, and this is a little movie that hopefully proves that dust is the cause of the red colours. So that grey moving line is the blue quasar plus some amount of dust, but don't worry about this. And hopefully what you see is that simply just dust reddening a blue quasar, you can actually recreate the shape of the majority of our red quasars very well. So I have done kind of quantified this, but in the paper I basically argue that the red colours can be explained by dust, which I've made sound obvious from this talk, but there are other things that can make something look red. They can just be intrinsically red. Host galaxies, so light from the galaxy is actually quite red. So if you have a very bright host galaxy, this can make the quasar light look much redder, and other things like this. But the simplest solution is dust, and we've proven that, as you'd expect, the simplest solution is normally the correct solution. Just in the last 5 minutes, I'll just talk about some of my future work. One of them is looking at DESI, which is the Dark Energy Spectroscopic Instrument, maybe you've heard of this because Durham is very involved in DESI. DESI is an instrument on the Mail telescope in Kitt Peak, Arizona. So this is the Mail telescope, so DESI's somewhere in there. I did have a chance to go out to Arizona and observe, but then that was in April 2020, so it was not a great time, which is a bit of a shame. And now they just do remote observing, and apparently that's easier and cheaper. So a bit sad, but it probably is in terms of global warming as well, it's probably for the best. Anyway, so DESI is a 5-year survey. It started last year. Durham's been very involved with a lot of the instrumentation has been done here, and we're involved in the science. And over the next 5 years, it's hoping to observe, I always remember the quasar number, it's about 3 million quasars. So remember me saying we use SDSS, which has 500,000 or 750,000. DESI is going to get 3 million quasars in five years. So it's pretty impressive. I think I'll say like 20 million galaxies. There's a lot more galaxies, but I don't care about the galaxies. And within DESI, I have a program that's an approved program that's searching for red quasars. So, and it's already observed a number of them. First of all of the imaging that kind of DESI's observations are based on is kind of publicly available. It's just a really cool website called Legacy Survey Viewer, and you can just get that up, and it has basically the whole of the Northern Hemisphere. If you want to have like an existential crisis, like look at this website and kind of zoom in and search for different galaxies. But I'm just going to zoom in on one area of the sky. So here we have a lovely spiral galaxy, but I don't care about that. Don't like galaxies. That little orange guy, that little dot there, is one of my red quasars that got observed last year. And we now have about 440 red quasar candidates, but we're hoping to get about 30,000 over the next 5 years. And the great thing about DESI is that it's going to more obscured and fainter systems. So we're finding red quasars that have much redder colours than what we could even observe in SDSS, and much fainter than what the limit of SDSS. So that's kind of what I'm working on at the moment, which is pretty exciting. But also with DESI, because it's an international collaboration, this is happening a bit more with telescope collaborations. Universities have to buy in, they have to pay a lot to be able to have data. So I'm just lucky that my PhD is at Durham, which is what we call a DESI institution. They paid a lot of money so that the astronomers can have access to any DESI data they want. But it kind of sucks now that I'm going to get hopefully a new job, and it might not be at a DESI institution, which means I won't actually be able to access DESI data. But unfortunately, there's quite a strong overlap between astronomy and politics, so not everything is kind of open access yet. Okay, and the next thing I'm going to do is look at some more radio data, this time from the Giant Meter Radio Telescope, or GMRT. And this is a radio telescope in Pune, Kodak, India. And the good thing about this is it takes lower frequency radio observations compared to what I've done before. If you like frequencies, my previous radio results have been 1.4 gigahertz. The data we've got from this is about 150 megahertz up to 1.4 gigahertz. So it's probing a different region. And what we're hoping to do is kind of construct sensitive radio SEDs, which will tell us, hopefully, is the radio emission due to winds or is it due to jets? And it should shed some light on this, but I won't go into detail how. But I was lucky enough to actually go out and take some observations. So this is what I had all week at the Telescope Institute in Pune. And it was curry 3 times a day. Did not get tired of it. I actually thought I would. I thought I'd get sick of curry, but no, it was amazing. Lovely curry. I realised I could have curry for every meal for the rest of my life. Here's a picture of B with 2 of the antenna. So GMRT consists of 30 meter diameter antenna, so I've already talked about radio data, that it's this interferometry where you link up all these dishes. And it's pretty cool because you could just walk around the site. What we hadn't realised when we were taking our really lovely sunset photos of the telescopes is there's actually quite a large leopard population there, which no one thought to tell us, but someone was like, oh, you're not going out in the evening or in the morning. We're like, yeah, we've been doing that all week. And they were like, yeah, that's peak leopard time. And I thought they were just winding us up. And I Googled it, and there's been a few, they do tend to attack toddlers more, so it's fine. But there's been a couple of leopard attacks. They weren't actually, they were genuinely concerned. So that put off my supervisor a little bit from walking around. But we didn't see a leopard, so it's fine. And yeah, this is me pretending to do some work in the control center, but it's actually these guys over here who are the employed telescope operators. So every time you go observing, you're the observer, but there's always telescope operators that actually get employed by the telescope and actually know what they're doing, whereas you're just kind of, I don't know, pretending. And finally, this is just a lovely, one of the sunset photos I took whilst not being attacked by a leopard. And that's it. Thank you very much. Are there any questions? It's fine if you don't, or you can come and talk to me afterwards if you don't want to ask.
Thank you.